total mechanical energy of a system is conserved. That is, the sum of kinetic and potential energy is a constant. Step through the process to see how the kinetic and potential energies change, but the sum of the two remains a constant. A pendulum is a good example of a conservative system. In the absence of friction, it will go on forever, converting potential energy and kinetic energy back and forth. As we move about the sun, and the sun moves about the universe, our orientation and velocity must vary with respect to this proposed ether frame. This is the Michelson-Morley experimental setup. If light travels at different speeds in different directions, along paths of equal length, then, when the beams from the two paths reunite, they will form an interference pattern. If, however, light travels at the same speed in all directions, no interference would be observed. In fact, no interference was observed, so no ether frame exists. Let's assume the ether frame moves relative to the Earth from left to right. Michelson-Morley used a half-silvered mirror to split a beam of light so that it travels in two different directions along two paths of equal length. This is the light beam before it is split. Moving in a perpendicular direction to the ether frame, this beam would be blown off course and would have to travel a little further. Traveling back down this path again, perpendicular to the ether, would also move this beam off course, if the ether existed. This beam, moving parallel to the ether and in the same direction, would increase its speed. This beam, again parallel to the ether, but moving in the opposite direction, would be slowed down. Here the two light beams are recombined together, and if they are in phase, they will constructively interfere. But if the speed was different in the two paths, they would combine to give an interference pattern. You know that when you look at the stars, you look back in time. The light from distant stars takes years to reach us. A light year is the distance that light travels in 1 year. If an explosion occurs far away, it takes time for the light to reach us. In this example, it takes the observer at the origin about 3 seconds to know that the explosion took place. We could synchronize clocks all over the universe, none of them moving relative to us. They will all read the same time. If an event happens close to 1 o'clock, then we will know the time the event actually happened. The time that you see something happened is different from the time the event actually occurred. Simultaneity is a relative concept which requires some thought to understand. It is simply based upon the fact that the speed of light is a constant, so moving and stationary observers see different things at different times. Watch the light from the lightning bolts travel. Both women see the bolt strike simultaneously. The train is stationary when these two bolts hit, and the light starts to propagate. Neither women have seen the bolts at this point. The light arrives simultaneously at the two observers, who agree that the bolt struck simultaneously. They are both in the same inertial frames. The train moves as the lightning strikes. Tanya is moving towards the front event, and Gertrude is not moving. Since Tanya is moving forward with the train, she catches up to the light coming from the front lightning strike, and therefore she sees the front bolt first. Now the light from both bolts arrives at Gertrude. She sees them, and she exclaims that both strikes are simultaneous. Finally, the light from the rear bolt reaches Tanya, and she disagrees that the bolts strike simultaneously, and they do not in her frame.